In September 2012, a signal left a spacecraft traveling through the darkness beyond our solar system. It took 17 hours to reach Earth. The data it carried described a place no instrument had ever directly touched. And when scientists read it, several of the numbers did not match what 40 years of theoretical work had predicted. The plasma density was roughly 40 times higher than models expected. The magnetic field was pointing in the wrong direction. And over the following months, something even stranger emerged. Waves of energy generated by our own star were rippling outward through what was supposed to be quiet interstellar space, disturbing the plasma for billions of miles in every direction. Voyager 1 had crossed into interstellar space, and what it found there has been systematically revising our understanding of the structure, behavior, and true complexity of the region where the solar system ends and the galaxy begins. To understand why these measurements matter, you need to know what scientists thought they were sending Voyager into. Our star constantly exhales. The solar wind is a continuous stream of charged particles flowing outward from the sun in every direction. Near the sun, that wind travels at close to 1 million miles per hour. As it moves farther out, it gradually slows, but it keeps moving, carving a vast bubble through the surrounding interstellar medium, the thin gas and magnetic fields that fill the space between stars. That bubble is the heliosphere. Everything inside it, every planet, every moon, every spacecraft humanity has ever launched, exists within this wind-carved cavity. The heliosphere does not end suddenly. As the solar wind pushes outward, it eventually reaches a distance where the pressure of the surrounding interstellar medium becomes strong enough to slow it dramatically. That transition point is called the termination shock. Voyager 1 crossed it in 2004. Beyond the shock, the solar wind continues moving, but slowly and turbulently. Scientists call this churning region the heliosheath, and beyond the heliosheath lies the heliopause, the true outer boundary of the heliosphere, where the last traces of solar wind pressure give way entirely to the interstellar medium. That is the boundary Voyager 1 crossed in 2012. And the boundary it crossed was nothing like the models described. Start with the heliosheath, the region Voyager spent years traveling through before it ever reached the outer boundary. The standard model described this as a compressed but relatively smooth layer of slowing solar wind. What Voyager's instruments found instead was something far more complicated. The magnetic field inside the heliosheath did not run in orderly lines. It folded back on itself in unexpected ways. Particle flows were uneven and irregular. And then came a discovery that no model had included at all. Scientists analyzing Voyager's data found evidence of enormous magnetic bubbles inside the heliosheath. These are structures where the solar magnetic field, instead of behaving like orderly parallel lines, folds and reconnects with itself, forming closed loops hundreds of millions of miles across. They cannot be seen directly, but their effect on how particles move through the region is measurable. When Voyager passed through them, the instruments registered distinct changes in both the local magnetic field and the count of particles passing by. Changes that only made sense if the region was filled with a kind of turbulent magnetic foam. The heliosheath, the buffer zone our spacecraft spent years crossing on its way out, more closely resembled churning froth than a calm transition layer. That has direct implications for one of the heliosphere's most important functions. The heliosphere acts as a partial shield against galactic cosmic rays. These are high-energy particles, mostly protons and atomic nuclei, accelerated to extreme velocities by supernova explosions, pulsars, and other violent processes occurring throughout the galaxy. A turbulent, irregular heliosheath makes the shield harder to calculate and less uniform than a clean bubble model would suggest. The actual cosmic ray protection our solar system provides is more uncertain than textbook models implied. There was something else that surprised scientists about the region approaching the outer boundary. The boundary itself was leaking. In the months before Voyager 1's confirmed crossing, its instruments detected repeated, sharp changes in particle counts. Low-energy particles from inside the solar system would drop, then surge, then partially reverse. The counts oscillated in a pattern, suggesting that the spacecraft was not approaching a clean, fixed wall. It was repeatedly passing through and partially back across a turbulent, shifting edge. The heliopause is moving. External pressure from the interstellar medium fluctuated, and when it fluctuated, the boundary location shifted with it. This was the first direct confirmation of something that models had theorized but never verified. The heliosphere breathes. It expands and contracts in response to changes in both the solar wind's output and the external pressure of the surrounding interstellar medium. During periods of high solar activity, stronger wind pushes the boundary farther out. During quieter periods, or when the interstellar medium locally increases in density, the boundary moves inward. That breathing has real consequences. As the boundary shifts, the cosmic ray flux reaching the inner solar system changes. These are particles energetic enough to damage both biological DNA and electronic systems. The heliosphere's breathing cycle is not an abstract property of distant space. It is an active variable in the radiation environment experienced by every planet inside it, including Earth. Beyond the boundary's mobility, there was its permeability. Charged particles from the solar wind were leaking outward through the heliopause into interstellar space, while neutral atoms from the interstellar medium were drifting inward. The filtering mechanism comes down to electrical charge. Neutral atoms, carrying no charge, pass through magnetic boundaries that deflect charged particles. Interstellar hydrogen atoms drift inward continuously, eventually gaining or losing an electron and becoming detectable inside the heliosphere. A spacecraft called IBEX, the Interstellar Boundary Explorer, mapped this neutral atom flow from Earth orbit, building a picture of the boundary structure that complemented what Voyager was measuring from inside it. What the two datasets revealed, combined, was a heliopause that leaks, breathes, and varies in thickness depending on which direction you measure. And one direction in particular had already produced a measurement that had stopped scientists cold long before Voyager's crossing. In 2009, IBEX published its first full-sky map of energetic neutral atoms arriving from the boundary region. Scientists expected a roughly uniform glow, perhaps brighter in some directions and dimmer in others, but broadly smooth. What the map showed instead was a ribbon, a bright, narrow band of emission curving across the entire sky in a sweeping arc, 2 to 3 times brighter than anything surrounding it. It encircled the solar system, and no existing model of the heliosphere had predicted it would be there. The ribbon runs roughly perpendicular to the direction of the local interstellar magnetic field. That geometry is the key to understanding it. When solar wind particles cross the heliopause and travel outward into interstellar space, some retain enough energy to keep going. Out there, the local interstellar magnetic field can curve their paths, bending them back toward the solar system. When those returning particles re-enter the heliosphere and shed their charge, they become neutral atoms traveling inward, and IBEX catches them. The ribbon, in this model, marks a region where the geometry of the external magnetic field is oriented at exactly the right angle to curve the largest number of returning particles back toward us. It is, in a sense, a map drawn in glowing particles that traces the shape and direction of the magnetic field pressing on our bubble from the outside. Think about what that means. An external magnetic structure extending far beyond our solar system and connected to the larger architecture of the galaxy is actively shaping the heliosphere. The boundary location, the thickness of the heliosheath in different directions, the overall geometry of our bubble, all of it is partly determined by a magnetic field existing between the stars. There is still scientific debate about the precise mechanism producing the ribbon. Alternative explanations have been proposed, but what is agreed upon is that it exists, that it is organized, and that it reflects something real and measurable about the external magnetic environment pressing on us from outside. After IBEX published its ribbon maps, the smooth, roughly spherical bubble of older models was replaced in most research with a more compressed, asymmetric structure. The leading edge, the side facing our solar system's direction of travel through the galaxy, is pushed inward by external field pressure. The trailing side extends outward behind us, stretched by our motion, which brings us to the second Voyager data point, because one crossing was not enough. Voyager 2 crossed the heliopause on November 5th, 2018, at roughly 119 astronomical units from our star, which works out to approximately 11 billion miles. Voyager 1 had crossed roughly 6 years earlier at approximately 121 astronomical units, but in a different direction. One data point became 2, and the differences between them were significant enough to demand explanation. Voyager 2 crossed in the southern hemisphere of the heliosphere. Voyager 1 had crossed in the northern hemisphere. The boundary at Voyager 2's crossing point was measurably warmer. The plasma just inside the heliopause on Voyager 2's side was hotter than what Voyager 1 had measured, and the crossing itself was slightly sharper and more abrupt. That temperature difference has no settled explanation. One possibility is that heat from interstellar space leaks inward through the permeable boundary at different rates in different locations. Another is that the interstellar medium simply has different properties in the direction Voyager 2 traveled compared to Voyager 1's path. The answer is genuinely open. What is clear is that the heliopause has regional character. It is not a uniform shell, but a surface that responds to local conditions on both sides simultaneously. The two crossings together confirm something that had been theorized, but never directly measured. The heliosphere is thicker on one side than the other, compressed where our solar system pushes into the surrounding interstellar medium, and stretched where it trails behind. Both Voyager craft crossed from roughly the flanks of this structure, in different directions. Even those two flanking crossings showed measurable differences. The full picture, with a compressed nose, an extended tail, and boundaries that vary in temperature and sharpness depending on location, looks less like a bubble and more like a comet shape. How long the tail extends is genuinely unknown. Some models suggest it stretches for hundreds of astronomical units behind us. Others suggest the tail may break up into separate lobes. No spacecraft has traveled down it to measure directly. Both Voyagers also confirmed something about the boundary layer itself. Right at the crossing point, in a thin zone on the inside of the heliopause, the plasma was extremely hot. Temperatures in that boundary layer reached tens of millions of degrees. That heat has to come from somewhere. The leading explanation involves solar wind particles being energized through interactions with interstellar plasma at the crossing point, though the exact mechanism is still being worked out. Beyond that thin, hot layer, both Voyagers entered the interstellar medium. And what Voyager 1 found there proved that interstellar space is not the empty, featureless silence that older models had implied. In April 2013, roughly 7 months after its confirmed crossing, Voyager 1 detected oscillations in the plasma surrounding it. The instrument that registered them, the plasma wave instrument, was measuring a specific frequency of electron vibration. That frequency allowed scientists to calculate the density of the plasma around the spacecraft. The detection itself was scientifically valuable. What made it remarkable was what triggered it. A powerful solar eruption had occurred in March 2013. The pressure wave it generated traveled outward through the solar wind, crossed the heliopause, and kept traveling into interstellar space, compressing the surrounding plasma when it arrived at Voyager's position, more than 12 billion miles from the Sun at the time. When that wave compressed the interstellar plasma, the plasma rang, the way a struck bell vibrates at a specific pitch. Scientists called these events plasma tsunamis. Voyager 1 detected at least 3 of them in the years following its crossing. Each one gave scientists a precise local measurement of interstellar plasma density, and it was through these tsunami-triggered measurements that the 40 times denser than expected figure was confirmed directly. The plasma tsunamis also change how we think about the relationship between stellar activity and interstellar space. Stars do not just influence their own systems. Powerful eruptions propagate past the heliopause and disturb the interstellar medium for billions of miles in every direction. In a galaxy full of stars, all of them erupting at different rates and intensities, the interstellar medium is constantly being disturbed from multiple directions simultaneously. It is not a static, uniform background. It has what you could reasonably call weather. Before Voyager could carry the story of interstellar space back to scientists, there was one more notable feature waiting for it to encounter on the way out. A feature that had already been hinted at from inside the heliosphere and confirmed from multiple spacecraft. A wall. Not a metaphorical one, but a physical compression of neutral hydrogen atoms that marks the nose of the heliosphere's interaction with the surrounding interstellar medium. Picture the heliosphere in motion. Our solar system is not stationary. It travels through the galaxy at roughly 52,000 miles per hour, relative to the surrounding local interstellar medium. The entire heliospheric bubble moves with it, pushing through the interstellar gas ahead. At the leading edge, where the heliosphere's magnetic boundary deflects most charged interstellar particles around its sides, neutral hydrogen atoms are not deflected. They drift forward and pile up just outside the heliopause, compressed and slowed by the interaction. This pileup forms a detectable layer of denser hydrogen sitting just ahead of the solar system in the direction of travel. Voyager 1 and Voyager 2 both detected a signal consistent with this hydrogen wall. Their ultraviolet instruments measured a faint excess of ultraviolet emission in the direction the solar system is heading. New Horizons, the spacecraft that flew past Pluto and is still traveling outward, confirmed the signal from its own position closer to the inner solar system. Its ultraviolet sensor detected the same faint glow in the same direction. 3 spacecraft, measuring the same feature from different positions, all returning consistent signals. The hydrogen wall is real. Why does this matter beyond confirming one feature at the edge of our solar system? Because the hydrogen wall is not unique to us. If our solar system creates one as it moves through the interstellar medium, then any star with a stellar wind moving through its local gas environment should produce the same kind of pileup outside its own heliopause equivalent. And if the hydrogen wall produces a detectable ultraviolet signature, we might be able to detect the outer boundary regions of other stellar systems from Earth, without ever sending a spacecraft near them. In 2022, a team of scientists analyzed Hubble Space Telescope data and found evidence of hydrogen wall signatures around a small number of nearby stars. The detections were statistically marginal and require further confirmation, but the technique is real and the candidates are compelling. This was the first observational evidence that we might be capable of detecting the outer boundary regions of other stellar systems from a distance. And that transforms what Voyager measured. The hydrogen wall is not just an interesting edge feature. It is a marker type that might allow us to survey stellar bubble boundaries across interstellar distances, mapping the outer boundaries of other solar systems using the same ultraviolet fingerprint that multiple spacecraft confirmed around our own. Inside the heliosphere, years before the boundary crossing, Voyager had already passed through a region that surprised scientists for different reasons. In 2010, Voyager 1 entered what the mission team called the stagnation region. The solar wind around it slowed nearly to a stop. Voyager was still inside the heliosphere, still inside the termination shock boundary, still surrounded by solar wind material. But that material had essentially ceased its outward flow. The explanation involves pressure balance. Beyond the termination shock, solar wind continues moving through the heliosheath, but at reduced speed. As it approaches the heliopause, the increasing external pressure of the interstellar medium pushes back harder. In the stagnation region, those two forces reach a rough equilibrium. The solar wind material is not gone. It is stacked up, compressed against the outer boundary, with nowhere left to go. What surprised scientists was how long and complex this region turned out to be. They had expected a relatively thin layer before the heliopause. Voyager traveled through the stagnation zone for roughly 2 years before it crossed the boundary. The magnetic field in that region also showed signs of turbulence and folding, with the same kind of magnetic bubble structures discovered elsewhere in the heliosheath, tangled and overlapping. There was evidence of active magnetic reconnection in the stagnation zone as well. This is a process where opposing magnetic field lines snap and relink, releasing energy. The same process drives solar flares closer to our star. Finding it operating at the heliosphere's edge changed the character of the boundary from a passive container to an energetically active interface, one that mediates and converts energy between the solar environment and the interstellar environment continuously. That distinction, passive versus active, changes what the heliosphere actually is. And to understand the interstellar environment that the heliosphere is actively interfacing with, you need to zoom out significantly, because the context turns out to span thousands of light years. Our solar system has been traveling through a specific region of interstellar space for the last several million years. A thin, warm cloud of gas that astronomers call the local interstellar cloud, informally known as the local fluff. It stretches roughly 30 light years across. Our solar system sits near one edge of it, and the fact that we are near the edge matters more than it might initially seem. The local fluff is a cloud of partially ionized hydrogen and helium gas, warmer and less dense than the average interstellar medium. It sits inside a much larger structure called the local bubble, a vast low-density cavity roughly 1,000 light-years across in our region of the Milky Way. The local bubble was carved out over millions of years by supernova explosions from massive stars that used to occupy this region of the galaxy. Those explosions drove shock waves outward into the surrounding interstellar gas. Over millions of years, as explosion after explosion followed in sequence, the expanding shock waves merged and pushed the gas outward, hollowing out a growing cavity. The result is the local bubble. Its walls are made of compressed, swept-up interstellar gas. Inside the bubble, the gas density is roughly 100 times lower than the galactic average. Our solar system has been inside this bubble for millions of years. Drifting through its low-density interior, the local fluff and the other warm clouds surrounding us are fragments and condensations floating inside the bubble's relatively empty interior. In 2022, a study using data from the European Space Agency's Gaia satellite, combined with other surveys, mapped the three-dimensional structure of the local bubble in detail. The research found that, essentially, all of the nearby, young, star-forming regions within a few thousand light-years sit on or near the surface of the local bubble's expanding shell. The shell's expansion, still ongoing at roughly 4 miles per second, has been compressing gas at its edges for millions of years. And that compressed gas is what eventually collapses under gravity to form new stars. The local bubble is, in a literal sense, a star factory powered by ancient stellar death. The very stars forming near us today, some of them still in the process of forming, owe their existence to the chain of supernovae that carve the cavity our solar system moves through. Voyager's journey exists inside this context. The interstellar medium it samples, just beyond the heliopause, is local bubble material, low-density gas shaped by millions of years of stellar explosions. The magnetic field Voyager, measured in interstellar space, is part of the local bubble's internal magnetic structure, which is itself a remnant of fields compressed and reorganized by those ancient explosions. And this context provides at least a partial explanation for one of the most puzzling of Voyager's crossing anomalies. When Voyager 1's magnetometer measured the interstellar magnetic field just outside the heliopause, the field direction was expected to shift significantly from the orientation of the solar magnetic field on the inside. Models built over decades predicted a clear angular difference. The field on the outside should point in a distinctly different direction. It did not shift the way models predicted. The interstellar magnetic field, measured by Voyager 1 just outside the heliopause, was oriented more closely to the solar field than expected. One possible contributing factor is exactly this shared history. The solar system and the surrounding interstellar medium both formed within the same regional magnetic environment, inside the local bubble. Their magnetic fields share a common origin in the ancient blasts that created the cavity. The fields are not randomly oriented relative to each other. They have a family resemblance, end quote. The IBEX ribbon also provided a partial reconciliation. The geometry of the ribbon's position in the sky points toward a specific orientation of the local interstellar magnetic field, and that orientation does reduce some of the discrepancy between what models predicted and what Voyager measured. Not entirely. The field direction question remains an open research area, but the context is richer and more connected than the pre-crossing picture allowed. There is a larger implication buried in all of this. Our solar system is near the edge of the local fluff, and therefore approaching a transition. Some models suggest we may exit the cloud within as few as 2,000 years. Others suggest the exit could come sooner, or that we may have already reached the edge. The uncertainty comes from imprecise measurements of the cloud's exact boundary. When our solar system exits the local fluff and enters a different region of the local bubble's interior, the external pressure acting on the heliosphere will change. If we move into a lower density region, the heliosphere expands. A larger heliosphere means more shielding from galactic cosmic rays. If we enter a denser region, the heliosphere compresses. A smaller heliosphere means more galactic cosmic radiation reaches the inner planets. Scientists studying ice cores from Antarctica and ocean sediment cores from the deep sea have found evidence of elevated cosmic ray flux at various points in Earth's geological past. Some of these episodes correlate with periods of increased atmospheric ionization and other environmental effects still being studied. Whether past changes in the heliosphere's size and shielding contributed to any of them is an active research question. The connection has not been confirmed, but the mechanism is physically plausible and taken seriously by researchers. Voyager's measurements of the interstellar medium just outside the heliopause give scientists the first real in situ sample of what the local fluff contains at the boundary with our heliosphere. Every measurement the spacecraft makes directly calibrates the models used to predict what will happen when our solar system moves into the next region of interstellar space. What Voyager found beyond the heliopause also allowed scientists to quantify, for the first time with real measurements, how effectively the heliosphere reduces the galactic cosmic ray flux reaching the inner solar system. When Voyager crossed the boundary, its instruments registered a jump in galactic cosmic ray intensity. Outside the heliopause, galactic cosmic ray intensity is roughly 2 to 3 times higher than inside the heliosphere, depending on the energy range being measured. That factor represents the actual, measurable shielding contribution of the heliosphere. Higher energy particles pass through more easily, but the lower energy population, which is the largest, is significantly reduced. Voyager's crossing data gave scientists a calibration point for understanding what the unmodulated flux looks like before the heliosphere filters it. For astronauts, that factor matters enormously. Missions within the heliosphere already expose crew members to elevated cosmic ray doses, particularly during periods of low solar activity, when the solar wind weakens and more galactic rays penetrate inward. Missions that might one day travel beyond the heliopause would encounter the full, unattenuated cosmic ray flux of the interstellar medium. The heliosphere is the barrier standing between that flux and everything inside it. The heliosphere also modulates the cosmic ray flux in a cycle tied to solar activity. During periods of high solar activity, the stronger solar wind deflects more galactic cosmic rays, reducing the flux inside the heliosphere. During solar minimum, the flux increases. This modulation was theorized for decades. Voyager's measurements gave scientists a reference point for calculating how much of the modulation the heliosphere is actually responsible for. For Earth specifically, galactic cosmic rays ionize the upper atmosphere and may play a role in cloud formation processes, atmospheric chemistry, and potentially climate on geological timescales. The relationship is complex and still debated among researchers, but the physical mechanism is real. The heliosphere is, in this sense, a variable filter with planetary consequences, and that filtering ability has likely changed significantly across Earth's history as the solar system moved through different regions of the galaxy. Now consider a broader question. If every star with a stellar wind creates a heliosphere equivalent, what do those other stellar bubbles look like? The technical term for the stellar bubble around another star is an astrosphere. The physics is identical to the heliosphere. Stellar wind pushes outward, meets the surrounding interstellar medium, creates a termination shock, a compressed boundary layer, and eventually a heliopause equivalent outer boundary. Before Voyager's crossing, models of astrospheres were built on our understanding of the heliosphere from the inside, combined with theoretical assumptions about what the boundary would look like. Now, with Voyager's direct measurements of the heliopause and the interstellar medium just outside it, scientists have a genuine ground truth calibration point for the first time. Massive hot stars with powerful winds can carve astrospheres stretching dozens of light years across. Older, cooler stars with weaker winds may have tighter, smaller astrospheres. Stars moving through denser regions of the interstellar medium have their bubbles compressed from the outside. The size and shape of a stellar bubble is a function of both the star inside it and the environment surrounding it. Researchers studying astrospheres around nearby stars use the Hubble Space Telescope to search for ultraviolet signatures of hydrogen walls. If a star is moving through the interstellar medium and creating a heliosphere-like bubble, the hydrogen wall at its leading edge should emit a faint excess of ultraviolet radiation. The 2022 detections around a small number of nearby stars marked the first time observational evidence for the outer boundary regions of other stellar systems emerged. The detections were marginal in statistical terms and require confirmation, but the technique is validated and the candidates are compelling. The astrosphere perspective also reframes how scientists think about planetary habitability. The heliosphere's shielding effect on cosmic ray flux is a relevant factor for life on Earth. A planet orbiting a star with a dramatically smaller or weaker astrosphere would experience a much higher galactic cosmic ray flux at its surface, depending on its atmospheric thickness and composition. A planet orbiting a star with a larger, stronger astrosphere could receive significantly less. When scientists model potentially habitable planets around other stars, the astrosphere's properties are one of several environmental variables that affect what actually reaches the planet's surface. The same logic applies across time. Our heliosphere has likely changed significantly over Earth's history. In the early solar system, our star's wind was stronger, creating a more powerful heliosphere that extended farther and blocked more cosmic radiation. As the star aged and the wind evolved, the heliosphere changed. And throughout all of it, the interstellar environment our solar system traveled through kept changing as we moved through different regions of the galaxy. Voyager gave us the first real measurement of where the heliosphere meets the galaxy. From that single set of measurements, we can extrapolate backward in time and outward in space, modeling what the heliosphere might have looked like in the past and what other stellar bubbles might look like from the outside. All of this, the plasma density anomaly, the magnetic field discrepancy, the IBEX ribbon, the hydrogen wall, the plasma tsunamis, the breathing boundary, the asymmetric structure confirmed by two crossings, has come from a spacecraft built with 1970s technology, launched when personal computers did not yet exist, designed for a mission through the outer solar system that ended in 1980. The primary mission was to photograph Jupiter and Saturn. By 1980, that job was finished. The planning documents for any mission beyond the outer planets were written as a hopeful afterthought, contingent on whether the instruments would keep working. They kept working for nearly 5 decades. Several of the original instruments had already failed or been shut down to conserve power by the time Voyager 1 crossed the heliopause. Among them was the plasma science instrument, which had stopped functioning properly in 1980, before the craft had even left the outer planet region. That instrument was designed to directly measure plasma density, temperature, and velocity. Its loss was significant, so scientists improvised. The plasma wave instrument, designed to detect electrical and magnetic oscillations in the plasma around the spacecraft, became a substitute. When plasma tsunamis from solar eruptions compressed the interstellar medium around the spacecraft and caused it to oscillate at a measurable frequency, the plasma wave instrument registered it. The frequency of those oscillations directly revealed the local plasma density through physics the original designers understood but had not planned for as a primary data source. The plasma density measurements that revealed the interstellar medium was 40 times denser than expected came from an instrument operating far outside its original specification, interpreted through a technique developed decades after launch. Voyager 2 retained a functioning plasma science instrument and could make direct plasma measurements in ways Voyager 1 could not. This is partly why Voyager 2's crossing data, despite coming 6 years later, added so much to what Voyager 1 had indicated. The two spacecraft, each with different surviving instruments, built a more complete picture together than either could have built alone. Power is now the limiting factor. Each spacecraft runs on a radioisotope thermoelectric generator, a device that converts heat from the radioactive decay of plutonium into electricity. Plutonium decays at a predictable rate. With it, the power output drops by roughly 4 watts per year. To compensate, the team at NASA's Jet Propulsion Laboratory has been systematically shutting down heaters and non-essential systems over the years, prioritizing the instruments that return the highest scientific value per watt of power consumed. The plasma wave instrument, central to the most significant interstellar measurements, is among those the team works hardest to keep running. The magnetometer, returning continuous data on the interstellar magnetic field, is another. The cosmic ray instruments continue counting particles from inside and outside the heliosphere, extending a data set that no other instrument in history has contributed to. By the late 2020s, the remaining instruments will likely no longer have enough power to operate and transmit usable data. The signal will fade, not all at once, but instrument by instrument, until the spacecraft becomes a silent object moving through interstellar space at roughly 38,000 miles per hour, with no way to report what it is encountering. That silence matters more than it might appear to. Nothing else humanity has launched is anywhere near Voyager's position or trajectory. No mission currently in development will reach the heliopause for at least 15 years, and the most ambitious proposal for following up on what Voyager started, the interstellar probe concept, has not yet been approved for development. The gap in direct interstellar measurements, when Voyager falls silent, will likely last for decades. The interstellar probe concept has been studied seriously by scientists at Johns Hopkins University Applied Physics Laboratory and was formally assessed in NASA's most recent Planetary Science Decadal Survey. The concept envisions a mission capable of reaching approximately 1,000 astronomical units from our star within 50 years of launch. That is roughly 6 times farther than where Voyager 1 is now, and far enough to look back and map the full 3-dimensional shape of the heliosphere from the outside. To achieve that range in a practical time frame, the mission would require a gravity assist from Jupiter and a close pass around our star to generate a powerful outward kick, similar to the technique used by the Parker Solar Probe, but aimed in the opposite direction. At that speed and trajectory, the probe could cross the heliopause in roughly 15 years, compared to the 35 years it took Voyager 1. The proposed scientific payload would include instruments that Voyager never carried. Modern plasma analyzers capable of direct measurement, dust detectors, neutral atom cameras, ultraviolet telescopes capable of imaging the hydrogen wall and mapping the heliosphere's shape from beyond it. For the first time, we could see our solar system's bubble from the outside, the way you can only fully understand the shape of a mountain by stepping far enough away from it to see the whole thing at once. The interstellar probe carries another goal as well. The cosmic microwave background, the faint thermal afterglow of the early universe, reaches instruments inside the heliosphere, slightly distorted, because it has to pass through the heliosphere's influence before arriving. A telescope positioned well beyond the heliopause could observe the cosmic microwave background without that interference, potentially clarifying measurements that have been the source of significant cosmological debate in recent years. The mission has strong scientific backing and real engineering feasibility. What it lacks is the political and budgetary decisions that govern space exploration. If it launches in the next decade, it could be returning data from interstellar space around the time Voyager falls silent. The questions Voyager raised would begin to get the answers they deserve. There is also a set of things Voyager 1 has not been able to measure, and that absence shapes what we still do not know. Without a functioning plasma science instrument, key properties of the interstellar medium around the spacecraft, including plasma temperature and flow velocity, can only be inferred indirectly. The picture is real, but incomplete. Properties of the medium Voyager is traveling through remain unmeasured because the right instrument is not operating. The missing measurements matter particularly for understanding how the interstellar medium flows around the heliosphere. Models predict that the interstellar medium streams past the heliosphere in a specific direction and at a specific speed relative to our solar system's motion through the galaxy. Ground-based observations and IBEX data provide indirect measurements of this flow, but a direct, In situ measurement of the interstellar plasma flow velocity from a spacecraft positioned in interstellar space would either confirm or challenge those indirect values with the weight of direct measurement. Voyager 2, with its working plasma science instrument, has added important constraints, but the full picture of interstellar medium flow dynamics around the heliosphere requires more data points, more positions, more directions. 2 spacecraft crossing one boundary region in 2 directions is a beginning. There was also genuine scientific debate, lasting more than a year after Voyager 1's crossing, about whether the spacecraft had actually entered interstellar space, or had instead entered a transitional pocket where the interstellar medium had briefly intruded into the heliosphere without the spacecraft having fully exited. That debate was real among researchers. It was resolved primarily through the plasma oscillation measurements triggered by the solar eruption tsunamis in 2013. When those waves arrived and revealed the local plasma density, the numbers matched interstellar medium values and did not match heliosheath values. The crossing was confirmed as genuine. That debate reveals something important about the nature of the boundary itself. It is complex enough that even with a spacecraft physically at the crossing location, the data required careful interpretation over an extended period before the scientific community reached consensus. The edge of the solar system is genuinely ambiguous in ways that earlier models did not fully accommodate. There is also the matter of the magnetic field direction discrepancy. It has a partial explanation in the shared magnetic history of the solar system and the local bubble. It has a partial reconciliation with the IBEX ribbon geometry, but it does not have a complete explanation that satisfies all the data simultaneously. It remains an open research question that will likely require either a future interstellar probe or significantly better remote sensing from within the heliosphere to resolve. The boundary between our solar system and the galaxy remains, in the most precise scientific sense, an active frontier. Voyager 1 is currently more than 160 astronomical units from our star, traveling deeper into interstellar space at roughly 38,000 miles per hour. Voyager 2 is farther back, having crossed the heliopause later and in a different direction, and continues adding data points to the only direct interstellar measurement dataset that exists. As long as their instruments operate, both spacecraft are adding to a record that no other instrument in history has contributed to. When those instruments fail, one by one, the spacecraft will continue transmitting engineering data for as long as the transmitters have power, reporting their own health from billions of miles away. Eventually, the transmitters will fail too, and the signals will stop. The spacecraft will not explode, will not decay, will not stop moving. They will simply become silent, continuing their journeys at roughly 38,000 miles per hour with no way to communicate, carrying everything we sent with them into a galaxy they have only just begun to cross. The team that currently maintains both Voyagers does so with documentation from a project that began in the 1970s, updated and revised across decades, carrying institutional knowledge that is increasingly rare. Scientists who have worked on the Voyager mission have done so for decades, in some cases their entire professional careers. The spacecraft are older than many of the people currently operating them. When Voyager finally falls silent, it will mark the end of something that has never quite existed before. The first generation of humanity's direct reach into interstellar space, conducted in real time with an active spacecraft returning data as it traveled through the unknown. Everything that follows will build on what was learned in those transmissions. So what, precisely, did Voyager prove? It proved that the heliosphere's outer boundary is real, measurable, and physically sharp in ways models had only partly predicted. The crossing happened. The data confirmed it. The boundary exists at a definite location with definite properties that can be measured directly. It proved that the interstellar medium, just beyond the heliopause, is denser, more magnetically structured, and more dynamically connected to events inside the heliosphere than the standard pre-crossing picture described. The plasma density anomaly, the magnetic field discrepancy, the plasma tsunamis from solar eruptions reaching deep into interstellar space, all of these are confirmed, data-backed findings that changed the models. It proved that the heliosphere is asymmetric. Two spacecraft crossing the boundary in two directions at two different times return different readings. The boundary's properties vary by location. The heliosphere is shaped by the specific pressure and magnetic environment pressing on it from each direction. It proved that interstellar space is not passive. It has structure, it has pressure waves and density variations. It has a magnetic field that connects to the larger architecture of the galaxy. The region beyond the heliopause is not empty silence. It is a medium with its own physical character, shaped by the same forces that shape everything else in the Milky Way. And it proved, by surviving and returning data from interstellar space at all, that spacecraft can operate for half a century and continue delivering science beyond every expectation. That is not a trivial result. It is a demonstration of engineering margin that shapes how scientists think about designing long-duration missions. The questions that remain open are not small ones. The precise magnetic field direction at the boundary and why it deviated from predictions. The full three-dimensional shape of the heliosphere's tail. The detailed properties of the local interstellar medium across larger distances. The connection between the local bubble's environment and the cosmic ray history of Earth across geological time. The precise mechanism producing the IBEX ribbon. The extent and rate of magnetic reconnection at the boundary, and whether it operates continuously or episodically. All of these require the kind of direct measurement that only an interstellar probe, designed from the start to answer these questions, can provide. The heliosphere is not just the edge of the solar system. It is the interface between our local star system and the larger galaxy. A dynamic, breathing boundary that shapes what reaches Earth, what the radiation environment of every planet inside it has been across geological time, and what our solar system looks like to any instrument examining it from the outside. Voyager measured it. That measurement took nearly 5 decades to complete, and it is still coming in. The faint signal still arrives at the Deep Space Network, delayed by more than 22 hours, carrying measurements from a region of space no other instrument has ever reached. Every data packet returned is being archived and analyzed with the knowledge that it may describe conditions in a region of space that no future instrument will sample for a generation. When the signal finally stops, the spacecraft will travel on, silent, carrying everything we sent with it into a galaxy it has only just begun to enter. There is a detail about the plasma density anomaly that deserves more time, because it is not just a number. The 40 times discrepancy represents a fundamental gap between what our best theoretical models of the interstellar medium predicted and what actually exists out there. Understanding why that gap existed tells us something important about the limits of modeling an environment you have never directly sampled. For decades, the standard picture of the interstellar medium just beyond the heliopause was built from 2 sources. The first was theoretical modeling of how the solar wind and the surrounding gas should interact at the boundary, using known physics applied to assumed initial conditions. The second was remote sensing, particularly ultraviolet observations of nearby interstellar gas made from Earth orbit and from spacecraft inside the heliosphere. Remote sensing is powerful, but it has a fundamental limitation. You are measuring light that has passed through an entire column of gas stretched between you and the source. Disentangling what is happening at the specific region just outside the heliopause from what is happening farther away in the interstellar medium requires assumptions. And those assumptions, it turned out, were not accounting for all the relevant physics. One factor that likely contributed to the discrepancy involves how the heliosphere interacts with the surrounding medium on a dynamic, time-averaged basis. The models assumed relatively steady-state conditions, but the heliosphere breathes, as Voyager's crossing data confirmed. It expands and contracts with the solar cycle. That breathing pumps material outward during expansion and pulls it back inward during contraction, affecting the local density of the medium just outside the boundary in ways that steady-state models do not capture. Another factor involves the local fluff itself, the warm interstellar cloud of our solar system currently occupies. The local fluff has slightly different properties than the average interstellar medium. It is warmer and less dense than the galactic mean, which should reduce the expected density just outside the heliopause. If the models overestimated the typical interstellar medium density, but also failed to account for the local fluff's properties correctly, the final prediction could diverge from reality in exactly the direction Voyager observed, but by a different mechanism than the intuitive explanation suggests. What the plasma tsunami measurements confirmed was that whatever the reason for the discrepancy, the interstellar medium just outside the heliopause has real, measurable, physical density that is well in excess of the theoretical baseline. The plasma is there. It has mass, pressure, and behavior. It pushes back against the heliosphere with force that exceeds what the models described. And that force shapes the heliosphere in ways that only direct measurement could reveal. Scientists have since revised their models of the heliopause region, incorporating the plasma density data from Voyager's tsunami-triggered measurements as a calibration constraint. The revised models produce a boundary that sits closer to where Voyager actually measured it, with a heliosheath that is somewhat thicker than earlier versions predicted. The models are better, but they would not be better without the direct measurements from a spacecraft that crossed the boundary and reported what it found. This is a recurring theme in planetary and heliospheric science. Models are only as good as their inputs and assumptions. When direct measurements contradict model predictions, the models improve. When you cannot make direct measurements because no spacecraft has ever been to that location, the models are what you have, and they can be wrong in ways you do not know they are wrong until the data arrives. Voyager's crossing was, in this sense, a calibration event for the entire field of heliospheric science. Every model of the heliopause, the heliosheath, the termination shock, and the outer heliosphere has been revised in light of Voyager's data. And every future mission to the outer solar system or to interstellar space will use those revised models as its baseline. There is a specific measurement category that deserves its own explanation: the magnetic field behavior at and near the boundary. The magnetic field story from Voyager's crossing is layered, and each layer connects to a different aspect of heliospheric and galactic physics. Inside the heliosphere, the magnetic field has a characteristic structure. The sun generates a magnetic field that extends outward into the solar wind, and the rotation of the sun causes this field to spiral outward like a pinwheel, a shape described by a mathematical pattern called the Parker spiral, after physicist Eugene Parker, who predicted it in 1958. That spiraling field fills the entire heliosphere and is the dominant magnetic structure inside it. At the termination shock, where the solar wind slows from supersonic to subsonic speeds, the magnetic field intensity increases because the plasma is compressed. The field in the heliosheath is therefore stronger than in the outer solar wind, but also more turbulent and tangled due to the chaotic nature of the post-shock flow. When Voyager crossed the heliopause, scientists expected the magnetic field to make a significant turn. The solar magnetic field, organized by the sun's rotation into its Parker spiral structure, should give way to the interstellar magnetic field, which is organized by entirely different forces. The large-scale structure of the galaxy, the remnant fields from supernova explosions, and the slow dynamics of interstellar gas clouds over millions of years. Models predicted this transition would involve a clear angular shift, a measurable rotation of the field direction as Voyager crossed from the solar-dominated environment to the interstellar environment. The predicted shift was significant enough that it was one of the key diagnostic signals scientists planned to use to confirm that the heliopause had been crossed. The shift happened, but it was smaller than predicted. The interstellar field on the outside of the boundary was more closely aligned with the solar field on the inside than the models expected. This was not a subtle discrepancy. It was a quantifiable departure from the standard model that required explanation. Several competing explanations emerged in the years following the crossing. Some researchers argued that the local interstellar magnetic field in our region of the galaxy is simply oriented differently from what remote measurements had implied, and that the IBEX ribbon data, combined with Voyager's direct measurements, was giving us our first accurate reading of the true field orientation in the local fluff. Others argued that the boundary region itself was doing something physically interesting, perhaps involving a layer of enhanced reconnection and field blending that was partially aligning the two fields across the boundary. A third explanation, which does not necessarily exclude the others, involves the shared magnetic history of the solar system and the local bubble. Both the solar magnetic field and the local interstellar magnetic field have their deep origins in the same regional magnetic environment. The local bubble's magnetic structure was shaped by the same supernova explosions that created the cavity. The gas and field that eventually formed our solar system did so within that larger magnetic context. If the two fields share a common ancestor in the sense of having been shaped by the same ancient events, they would not necessarily be pointing in random directions relative to each other. They would have a tendency to be more aligned than models assuming randomly oriented fields would predict. This explanation is suggestive, but not proven. The magnetic field direction question remains one of the genuinely open problems in heliospheric physics. Resolving it definitively will likely require either a future interstellar probe with modern magnetometer instrumentation, or significantly better remote sensing of the local interstellar magnetic field from inside the heliosphere. What is not in doubt is the significance of the measurement itself. Voyager 1's magnetometer, an instrument that was not expected to be operating 5 decades after launch, delivered the first direct measurement of the interstellar magnetic field outside our heliosphere. That measurement constrained the range of possible explanations and forced the field to confront a discrepancy it could not explain away without new physics or revised assumptions. Let us also spend time on the termination shock itself, because it is a feature of the heliosphere that rewards careful attention, and because Voyager's crossings of it in 2004 and 2007, before the heliopause crossing, revealed surprises of their own. The termination shock is the location where the solar wind transitions from supersonic to subsonic flow. It is called a shock because the transition is abrupt, similar in principle to the sonic boom produced when an aircraft crosses the sound barrier, though the physics in the space environment involves plasma and magnetic fields rather than neutral air. Before Voyager crossed it, scientists had several predictions about the termination shock's properties. They expected it to be a relatively clean, sharp boundary. They expected the magnetic field to compress significantly across it as the decelerating plasma piles up on the downstream side. And they expected the cosmic ray intensity to change across it in a predictable way. Some of these predictions held. The magnetic field did compress across the shock. The cosmic ray intensity did change. But the shock turned out to be more dynamic and variable than models described. In the years before Voyager 1 crossed the termination shock, its instruments detected what appeared to be multiple crossings of the shock boundary, suggesting that the shock was moving back and forth across the spacecraft's position as the solar wind pressure fluctuated. This was a preview of the boundary mobility that Voyager would observe even more dramatically at the heliopause. The termination shock, like the heliopause, is not fixed. It moves in response to changes in the solar wind and in the external medium. When Voyager 1 finally crossed the termination shock in 2004, at roughly 94 astronomical units from the Sun, the data showed a complicated, multi-layered structure. The transition took place over a period that suggested the boundary was more extended than simple shock models predicted. And the way energetic particles were accelerated at the shock was different from what the models described. The termination shock was expected to be an efficient particle accelerator. Solar wind particles crossing the shock from the inside can be reflected back, gain energy, cross again, and repeat the process in a feedback loop called diffusive shock acceleration. This is the same mechanism thought to operate in supernova remnants and other astrophysical shocks, accelerating particles to high energies. The termination shock should therefore produce a population of energetic particles just inside and just outside its boundary. What Voyager found was that the shock was a more complicated and less efficient accelerator than expected. The distribution of particle energies across the shock did not match the standard diffusive shock acceleration model cleanly. There were additional particle populations that required additional explanations. Later work suggested that the termination shock has a more complex, three-dimensional structure than a simple spherical surface, with variations in shock strength and geometry depending on direction. These variations would affect how efficiently particles are accelerated at different locations on the shock surface. The two Voyagers, crossing the shock in different years and at slightly different positions, sampled a shock that was dynamically variable, both in time and in space. The termination shock data fed directly into models of cosmic ray acceleration in the heliosphere, and, by extension, into models of how astrophysical shocks in general accelerate particles. Every shock in the universe, from the bow shocks of magnetized planets to the blasts of supernova remnants expanding into the interstellar medium, operates on similar principles. Voyager gave scientists a shock they could study in detail from a spacecraft traveling directly through it. Beyond the termination shock, in the heliosheath, Voyager spent years measuring a region that turned out to be far more complex than the smooth, compressed transition layer of older models. Let us look more closely at the magnetic bubble structures discovered there, because they reveal something fundamental about how magnetic fields behave in the outer heliosphere. The magnetic bubbles form through a process called magnetic reconnection, the same process that operates at the Earth's magnetopause, in solar flares, in the stagnation region near the heliopause, and apparently throughout the heliosheath. The basic mechanism involves two regions of magnetic field pointing in opposite directions. When those regions are pushed together by plasma pressure, the opposing field lines can break and reconnect with each other in a new configuration. This releases stored magnetic energy and changes the topology of the field. In the outer heliosphere, the Parker spiral magnetic field has a characteristic property that makes it prone to reconnection. At specific latitudes in the heliosphere, the field direction reverses across a thin sheet called the heliospheric current sheet. This sheet wraps around the entire heliosphere, and as the solar wind carries it outward, it becomes increasingly folded and distorted. In the outer heliosphere, where the solar wind has been traveling for more than a decade, and where the current sheet has been folded and stretched by variations in the solar wind output across multiple solar cycles, the geometry becomes favorable for large-scale reconnection. Field lines of opposite polarity are pushed together. They reconnect. Closed magnetic loops form, detached from the broader field structure and containing trapped plasma. The result is the foam-like structure of magnetic bubbles that Voyager detected in the heliosheath. Rather than a smooth, radially organized magnetic field, the outer heliosphere contains a complex tangle of closed loops, partially open field lines, and regions of reconnection occurring continuously. This magnetic complexity matters for several reasons. First, it affects the propagation of galactic cosmic rays through the heliosheath. Cosmic rays trying to reach the inner heliosphere must navigate this complex field structure, scattering off irregularities and being trapped in closed loops for extended periods before eventually drifting inward. The heliosheath's magnetic foam makes it a more effective cosmic ray scatterer than a smooth, ordered field would be. Second, the magnetic bubbles trap solar wind plasma inside them, preventing it from flowing freely outward. This contributes to the stagnation region near the heliopause, where the solar wind velocity drops nearly to zero. The plasma is not simply stopped by external pressure, it is also trapped in a complex magnetic structure that prevents organized outward flow. Third, the energy released by reconnection in the heliosheath contributes to heating the plasma in that region. The heliosheath is warmer than it would be if the plasma were simply compressed adiabatically as it passes through the termination shock. The excess heating comes partly from reconnection events, distributing magnetic energy into particle thermal energy throughout the heliosheath volume. All of this is directly relevant to how scientists model other stellar systems. Every star with a stellar wind should have a heliosheath equivalent, and that heliosheath should have similar magnetic complexity if the star's field has similar properties to ours. The magnetic bubble structures in our heliosheath are not a quirk unique to our solar system. They are a generic prediction of how stellar wind magnetic fields evolve in the outer regions of astrospheres. Now consider something that has not received as much attention as the plasma density or the magnetic field anomalies, but that connects everything together in a way that is genuinely striking: the timing, Voyager 1 was launched in September 1977. It crossed the termination shock in 2004, 27 years after launch. It crossed the heliopause in 2012, 35 years after launch. It detected its first plasma tsunami in 2013. It is now more than 48 years into its journey, still transmitting, still measuring. That timeline means the instruments operating in interstellar space right now are the same instruments that were built and calibrated before the first personal computer was commercially available, before the internet existed in any recognizable form, before GPS satellites existed, before the space shuttle flew its first mission. The engineering margins built into those instruments, the conservatism in the design, the robustness of the nuclear power source, the reliability of the communication systems, all of it turned out to be sufficient, not just for the planned 4-year mission to Jupiter and Saturn, but for 5 decades of operation, in conditions ranging from the familiar environment near the outer planets to the completely unprecedented environment of interstellar space. This is not an accident. The engineers who built Voyager knew they were working at the frontier of what was achievable in 1977. They built in margin because they understood the limits of their own knowledge. They could not predict every environment the spacecraft might encounter. They could not know exactly how long the plutonium would last, or exactly how the cold of deep space would affect the electronics. So they built in margin. They tested aggressively. They designed for contingency. The result is a machine that has outlasted its designers' most optimistic predictions by decades. And because it outlasted those predictions, it was still operating when it reached the heliopause. And we got data from interstellar space that we would otherwise have had to wait decades more to obtain. The story of Voyager is, among other things, a story about the value of engineering conservatism in exploration. You do not know what you will encounter. You cannot predict what will go wrong or what will go surprisingly right. Building in more margin than you think you need turns out, over and over in the history of space exploration, to be the decision that makes the science possible. Consider also what it means operationally to communicate with a spacecraft at Voyager 1's current distance. The signals Voyager transmits travel at the speed of light. At the spacecraft's current distance of more than 160 astronomical units, those signals take more than 22 hours to reach Earth. Any instructions sent to the spacecraft takes more than 22 hours to arrive. Any response to that instruction takes another 22 hours to come back. A simple command and confirmation exchange takes nearly 2 days. This means the team operating Voyager cannot manage it in anything resembling real time. They plan ahead. They send sequences of instructions that the spacecraft executes autonomously over extended periods. The spacecraft has been operating in this semi-autonomous mode for most of its mission. When an anomaly occurs, by the time scientists learn about it and send a corrective instruction, the situation has been developing for nearly 2 days already. In 2023, this scenario played out dramatically when Voyager 1 began sending back garbled engineering data due to a fault in one of its onboard computers. The team at NASA's Jet Propulsion Laboratory had to diagnose the problem from 22 light-hour-old data to devise a solution using software and documentation from the 1970s, test the solution in simulations, and then send the corrective instruction and wait more than 22 hours to find out if it worked. The fix was eventually successful. The spacecraft resumed normal operations. But the episode illustrated exactly how much skill, patience, and institutional knowledge goes into keeping a 50-year-old spacecraft operational at the edge of the solar system. The team that pulled off that repair was working with documentation written before most of them were born. They were debugging software that predates modern programming languages. They were solving a problem on a computer system for which no replacement parts exist and no equivalent test environment can be built. And they succeeded. That is worth pausing on. The scientific achievements of Voyager are extraordinary, but the engineering and operational achievements that made those scientific measurements possible are equally remarkable. Now, there is one more thread to pull on before we reach the implications and the open questions. It involves the local bubble, the structure in the galaxy that surrounds our entire local region of space, and what it tells us about where we are in the Milky Way's history. The local bubble is roughly 1,000 light-years across in the local region of our galaxy. We are inside it. The solar system has been inside it for millions of years, and the fact that we are inside it has direct consequences for the heliosphere's structure and behavior. The interior of the local bubble is far less dense than the average interstellar medium. This low density means the external pressure acting on the heliosphere is lower than it would be in a typical interstellar environment. Our heliosphere is therefore larger than it would be if our solar system were sitting in a denser region of the galaxy. A solar system embedded in a dense molecular cloud, for instance, would have a heliosphere compressed to a fraction of its current size. A larger heliosphere means more shielding. More shielding means fewer galactic cosmic rays reaching the inner planets. The cosmic ray flux that reaches Earth today is partly determined by the local bubble's existence. We are living in a region of the galaxy that is unusually quiet in terms of interstellar medium density, and that quietness is a direct consequence of a series of supernova explosions that ended millions of years ago. If those supernovae had not occurred, or if our solar system were located in a different region of the galaxy, the heliosphere would be different in size and structure. And a different heliosphere means a different cosmic ray environment at Earth's surface. Whether that would have had measurable biological or geological consequences across Earth's history is an active research question. The mechanism is physically sound. The observational evidence for past cosmic ray flux variations is real, even if the connection to specific geological or biological events remains uncertain. The local bubble is also, as the 2022 Gaia-based study showed, still expanding. Its shell is moving outward at roughly 4 miles per second, driven by the residual pressure of ancient supernova shocks. As the shell expands, it compresses gas at the bubble's edges. That compressed gas collapses under gravity and forms new stars. Some of those new stars are forming right now, in the star-forming regions visible in nearby constellations. Our solar system's existence was enabled by the star-forming process in an earlier era. The ancient stars that died and created the local bubble were part of the same broad population of stars that enriched the galaxy with heavy elements. Elements that were incorporated into our solar system when it formed. The oxygen in Earth's atmosphere, the iron in its core, the calcium in its rocks, all of it was forged in stars that lived and died before our sun was born. And when those stars died in supernovae, they did not just release elements into the galaxy. They also created the cavity we now live inside. We are, in a very literal sense, children of the same process that carved our current home in the galaxy. Voyager's measurements of the interstellar medium just outside the heliopause are sampling the innermost layer of this ancient, vast structure. The low-density gas it measures in interstellar space is local bubble interior material. The magnetic field it samples is local bubble magnetic field, shaped by millions of years of stellar evolution in our region of the galaxy. The cosmic rays it counts, both inside and outside the heliopause, are produced by sources distributed throughout and beyond the local bubble, filtered and modified by the bubble's magnetic structure. Understanding Voyager's data requires understanding the local bubble. Understanding the local bubble requires understanding the history of stellar evolution in our region of the Milky Way over the past tens of millions of years. The data from a small spacecraft launched by humans in 1977 connects directly to the billion-year history of the galaxy. That connection is not metaphorical. It is physical. The numbers Voyager's instruments record are determined by processes operating at galactic scales across geological timescales. What appears to be a specialized heliospheric physics measurement is, when you follow the physics far enough, a reading of galactic history. This is one of the reasons the heliophysics community regards the interstellar probe concept with such seriousness. Voyager gave us one data point from one crossing, with aging instruments that could not measure everything. An interstellar probe with modern instrumentation, capable of measuring plasma density, temperature, velocity, composition, magnetic field direction and strength, neutral atom flux, dust properties, and the shape of the heliosphere from the outside, we would transform our understanding not just of the heliosphere, but of the local interstellar medium, the local bubble, and the interstellar environment in our region of the galaxy. The science case is strong. The engineering feasibility is well studied. What it awaits is the same kind of decision that authorized the Voyager missions in the first place. The recognition that some questions are important enough, and some opportunities rare enough, that it is worth the investment to go and find out. Voyager went to find out. It found more than anyone planned for. The questions it raised are worth answering. The plasma density in the local interstellar medium, the true orientation of the local interstellar magnetic field, the full three-dimensional shape of the heliosphere, including the tail nobody has ever sampled, the properties of the interstellar medium across the distances relevant to understanding how our solar system's environment will change as it continues moving through the local bubble and eventually exits it, the hydrogen walls of other stellar systems, the cosmic ray environment beyond the heliosphere on spatial scales larger than Voyager can currently probe. These are not abstract scientific questions. They connect to the radiation environment of Earth, to the conditions under which life evolved here, to the range of environments that planets around other stars might experience, and to the place of our solar system in the larger architecture of the galaxy. Voyager measured the first layer of answers. The instruments are still running. The signal is still coming in. Every data packet that arrives at the Deep Space Network's giant antennas carries information from a region of space that no human-built instrument had ever reached before 2012. When the signal stops, the archive will remain. Scientists will continue extracting meaning from Voyager's data for decades, refining their understanding of what the spacecraft actually encountered and what it means for everything from heliospheric modeling to astrobiology to cosmology. And eventually, if the interstellar probe concept is funded and launched, there will be a new signal arriving from interstellar space. A signal from a spacecraft that was built knowing what Voyager found, designed to answer the questions Voyager raised, carrying instruments capable of measuring what Voyager could not. When that day comes, scientists will use Voyager's data as the baseline against which to compare everything the new measurements reveal. The two sets of data will together define what we know about interstellar space in our region of the galaxy. One data set from the only mission that has ever been there, the other from the first mission designed from the beginning to go there and tell us everything Voyager could not. For now, the signal still arrives, delayed by more than 22 hours, carrying measurements from 160 astronomical units away and growing, from a spacecraft older than most of the people tracking it, still adding, day by day, to the only direct data set of interstellar space that humanity has ever built. That is what Voyager did. That is what it is still doing. And that is why its silence, when it comes, will be felt not just by the scientists who have spent their careers listening to it, but by everyone who has ever looked up at the night sky and wondered what is out there past the edge of our own small corner of the galaxy. Let us go deeper into something that sounds simple, but opens into one of the most complex topics in heliospheric science. Why does the heliosphere have the shape it does? And how confident are we in our picture of that shape? The intuitive image most people have of the heliosphere is a sphere, a ball of influence centered on the sun, extending outward equally in all directions. That picture is wrong, and it has been known to be wrong for a long time. But getting the details of the shape right has turned out to be harder than almost anyone expected. The first complication is motion. Our solar system is not sitting still in the galaxy. It moves at roughly 52,000 miles per hour relative to the surrounding local interstellar medium, roughly the average of the relative velocities between our solar system and the clouds of gas surrounding it. That motion means the heliosphere is constantly plowing through interstellar material on one side and leaving a wake on the other. Think of it like a jellyfish moving through water. The front of the jellyfish compresses the water ahead of it. The back of the jellyfish leaves a long trailing wake. The heliosphere's leading edge, the side facing our direction of motion through the local interstellar medium, is pushed inward by the ram pressure of the interstellar gas sweeping past it. The trailing side is stretched outward into a long tail. This basic asymmetry was known before Voyager crossed the heliopause, but the details of the tail shape, its exact length, whether it is a smooth, continuous extension or whether it breaks up into discrete lobes farther out, remained uncertain. A paper published in 2015 suggested, based on energetic neutral atom maps from IBEX, that the heliotail might be relatively short and structured into 4 distinct lobes rather than a smooth, elongated comet shape. The results were controversial. Other analyses of the same data reached different conclusions. The tail shape remains one of the genuinely open questions in heliospheric science. The second complication is the interstellar magnetic field. This is not the solar magnetic field. This is the field that exists in the interstellar medium outside the heliosphere, generated and maintained by the large-scale dynamics of the galaxy and shaped locally by the magnetic history of the local bubble. That field presses on the heliosphere from the outside and reshapes it. A magnetic field pressing on a magnetized bubble from the outside does not just compress it uniformly, it compresses it asymmetrically, depending on the angle between the field and the bubble's surface at each point. Where the field is perpendicular to the surface, the magnetic pressure is strongest. Where the field is more nearly parallel to the surface, the pressure is less. The result is a heliosphere that is not just asymmetric due to its motion through the interstellar medium, but also twisted and compressed in a pattern determined by the direction and strength of the external magnetic field. The IBEX ribbon, which runs roughly perpendicular to the local interstellar magnetic field direction, provided the first good observational constraint on the field's orientation. Combining that constraint with Voyager's direct magnetometer measurements outside the heliopause gives scientists their best current estimate of how the external field is oriented, and therefore how it is shaping the heliosphere. But here is the complication. The magnetic field direction that Voyager measured just outside the heliopause and the field direction that IBEX's ribbon geometry implies are not identical. They are similar, and they point in roughly the same general direction. But they are not the same measurement. They were made differently, and they do not agree perfectly. This disagreement might mean that the local interstellar magnetic field is not uniform over the scale of the heliosphere. It might mean that the boundary region involves local field modification through the same reconnection processes that operate elsewhere at the heliopause. It might mean that the measurement techniques, one direct and one inferred from particle observations, have systematic biases that need to be understood. Or it might mean something more interesting, that the heliosphere is embedded in a region where the interstellar magnetic field has a gradient, changing direction or strength across the scale of the heliosphere itself. Any of these explanations would be scientifically significant. None of them can be definitively chosen with the current dataset. The interstellar probe, with its modern magnetometer and its ability to map the magnetic field at multiple positions outside the heliopause as it travels outward, would provide the measurements needed to distinguish between them. There is also a third complication in the heliosphere's shape that receives less attention than the motion asymmetry and the magnetic pressure, the north-south asymmetry driven by the Sun's own magnetic field structure. The Sun's magnetic field is not uniform. It has a north and south magnetic pole, like Earth, and the orientation of the solar magnetic field relative to the interstellar magnetic field affects how the heliosphere interacts with the external medium at different latitudes. The heliospheric current sheet, the thin surface where the magnetic field changes polarity, is tilted relative to the solar equatorial plane and wobbles as the Sun rotates. All of these internal field complexities propagate outward through the solar wind and affect the heliosheath and heliopause at different latitudes in different ways. Voyager 1 and Voyager 2 crossed the heliopause at different latitudes, as we have discussed. The differences they measured, including the temperature difference and the sharpness of the crossing, likely reflect this latitudinal variation in the heliopause's properties. But with only 2 data points, distinguishing between effects due to latitude, effects due to the different crossing times with their different solar cycle phases, and effects due to genuine spatial variation in the local interstellar medium is extremely difficult. Scientists have done their best with the data available. the models have improved significantly. But the full three-dimensional picture of the heliosphere's shape, its tail, its asymmetry, and its latitudinal variation remains incompletely constrained by direct measurement. This is precisely the scientific justification for the Interstellar probe mission that has been under discussion for decades. Not just to go farther, but to go in a different direction, to measure the heliopause from a different angle, and to look back from outside and image the heliosphere's full three-dimensional structure using the neutral atom cameras that modern technology makes possible, but that Voyager's 1970s instrumentation could not carry. From inside the heliosphere, we can study the heliosphere as a swimmer can study the ocean from within the water. You can measure what is immediately around you. You can feel the pressure and the currents, but you cannot see the shape of the waves from above. The interstellar probe concept would allow us to surface, look back, and see the full shape of the structure we have been living inside for the entire history of our species. Now let us go back to something closer to Earth, literally, and think about what Voyager's measurements tell us about the radiation environment we live in, and the ways it has varied across our planet's history. Galactic cosmic rays arrive at Earth continuously. They are not a single type of particle at a single energy. They are a spectrum, ranging from relatively low-energy protons carrying energies of a few 100 million electron volts, up to extraordinarily energetic particles carrying energies of more than 10 to the 20th power electron volts, which works out to more than 10 billion electron volts, or about 10 billion electron volts per particle. At the lower end of this spectrum, the heliosphere provides significant shielding. The solar wind's magnetic field scatters and deflects lower energy particles, preventing many of them from penetrating to the inner heliosphere. The termination shock and the heliosheath add additional scattering. The result is that the cosmic ray flux at Earth is substantially lower than the flux in interstellar space for the lower energy population of particles. At the higher end of the energy spectrum, the heliosphere provides essentially no shielding. The most energetic cosmic rays, the ones with energies exceeding about 10 to the 18th power electron volts, or 1 billion electron volts, travel in such straight lines and carry so much energy that the heliosphere's magnetic field barely deflects them at all. These ultra-high energy cosmic rays arrive at Earth with roughly the same flux they have in interstellar space. The particles that Earth actually receives, then, are a mix. The very high energy cosmic rays that the heliosphere cannot stop, and the lower energy cosmic rays that get through during periods when the heliosphere's shielding is less effective, such as during solar minimum, when the solar wind weakens. Voyager's crossing allowed scientists to measure the cosmic ray flux just outside the heliopause and compare it directly to the flux measured inside the heliosphere. The roughly 2 to 3 times increase in flux outside the heliopause confirms the shielding contribution of the heliosphere for the lower energy particle population. More importantly, it gives scientists a calibration point for the unmodulated galactic cosmic ray flux, the baseline against which the heliosphere's variable shielding can be measured. This calibration matters for paleoclimate research. Galactic cosmic rays interact with Earth's atmosphere, producing secondary particles that cascade downward and eventually reach the surface. Some of these secondary particles are radioactive isotopes, including beryllium-10 and chlorine-36, which are produced when cosmic rays strike nitrogen and oxygen atoms in the upper atmosphere. These isotopes eventually reach Earth's surface and are incorporated into sediments, ice cores, and other geological records. By measuring the concentration of these isotopes in ancient sediments and ice cores, scientists can infer how the galactic cosmic ray flux at Earth has varied across geological time. Higher concentrations indicate higher cosmic ray flux. Lower concentrations indicate lower flux. And since the heliosphere modulates the cosmic ray flux, changes in the isotope record can, in principle, reflect changes in the heliosphere's shielding effectiveness. This is where the story becomes genuinely interesting. Several periods in Earth's geological past show anomalous spikes in the cosmogenic isotope record, periods when the cosmic ray flux reaching Earth was higher than normal. Some of these periods correlate broadly with intervals of reduced solar activity. The connection between solar activity heliospheric shielding, and cosmogenic isotope production is straightforward for solar cycle timescales. But some of the anomalies in the geological record appear to occur on timescales of millions of years, much longer than the 11-year solar cycle, or even the longer-term trends in solar activity. These longer period variations might reflect our solar system's passage through different regions of the galaxy with different interstellar medium densities and different cosmic ray source distributions. As our solar system moves through the galaxy over millions of years, the external pressure on the heliosphere changes, the heliosphere's size changes, and the cosmic ray flux reaching Earth changes with it. A particularly interesting period in this context is roughly 2 to 3 million years ago, when Earth entered the Pleistocene ice ages. The timing coincides, roughly, with geological evidence suggesting our solar system may have passed through or near a region of denser interstellar medium. Whether this is coincidence or cause and effect is not established, but the mechanism is physically plausible, and researchers are actively investigating it. Voyager's measurements of the current interstellar medium just outside the heliopause provide the baseline for modeling how the heliosphere would respond to different interstellar environments. If the external pressure were higher, say because our solar system were passing through a denser cloud, the heliopause would be pushed inward. The heliosheath would be thinner. The shielding effectiveness of the heliosphere would decrease. More galactic cosmic rays would reach the inner heliosphere. How much would reach Earth depends on how much the heliopause moves and how the heliosheath's magnetic structure changes in response. These are calculations that require the kind of calibrated model that Voyager's data makes possible. Without the direct measurements from the heliopause crossing, the models are purely theoretical. With Voyager's data, they are calibrated against reality. There is another thread worth following here, one that connects heliospheric physics to the question of life elsewhere in the galaxy. When scientists think about the habitability of planets around other stars, they tend to focus on the obvious factors: distance from the star, temperature, atmospheric composition, water. But the radiation environment at the planet's surface is equally important and often overlooked. A planet's surface radiation environment is determined by multiple factors simultaneously: the star's ultraviolet and X-ray output, the planet's atmospheric thickness and composition, the planet's magnetic field strength, and the galactic cosmic ray flux filtered by the stellar system's astrosphere. A planet orbiting a star inside a robust astrosphere with a thick atmosphere and a strong magnetic field might have a surface radiation environment very similar to Earth's, even if its other properties are quite different. A planet orbiting a star with a weak astrosphere in a region of the galaxy with high galactic cosmic ray flux and with a thin atmosphere and weak magnetic field might experience surface radiation levels that would make complex life very difficult. The astrosphere factor is particularly interesting because it depends not just on the star itself, but on where in the galaxy the star is located. Stars in the galactic plane, near the spiral arms where supernova rates are higher and the interstellar medium is denser and more turbulent, would have their astrospheres compressed and battered in ways that reduce their shielding effectiveness. Stars in the galactic halo, far from the plane, would have their astrospheres expanding into a lower density medium, but might also be in a region with different cosmic ray source distributions. The galactic habitable zone, a concept in astrobiology that tries to identify which regions of the galaxy are most favorable for life, is partly defined by these considerations. Regions too close to the galactic center have higher radiation rates, more frequent supernovae, and more gravitational perturbations. Regions too far from the galactic center may lack the heavy elements produced by stellar evolution over billions of years. The intermediate zone, the region that includes our solar system, is considered more favorable. But within that intermediate zone, the specific location matters. Whether your solar system is inside a low-density bubble like the local bubble, or embedded in a denser region of the interstellar medium, affects the astrosphere's size and therefore the cosmic ray flux filtering. Our solar system's position inside the local bubble is, in this framework, a potentially important detail of our habitability. We live in an unusually low-density region of the interstellar medium, created by ancient stellar explosions. That low density allows our heliosphere to be larger than it would otherwise be, providing more shielding against galactic cosmic rays. This is not the dominant factor in Earth's habitability, but it is a real one. Voyager's measurements, by characterizing the local interstellar medium and the heliosphere's response to it, contribute directly to this astrobiology framework. They give us measured values for the local interstellar plasma density, the local magnetic field strength and direction, and the cosmic ray flux, both inside and outside our heliosphere. These measured values are inputs to models of astrospheric shielding effectiveness for different stellar types in different galactic environments. The question of whether life is common or rare in the galaxy is one of the most important open questions in science. The answer depends partly on how many planets have the right combination of factors to support life across geological timescales. Astrospheric shielding is one of those factors. Voyager's data, combined with the hydrogen wall detections from Hubble and the IBEX ribbon observations, provides the observational foundation for understanding how that factor varies across stellar systems. The connections spread outward from a single spacecraft's measurements into questions about the structure of the galaxy, the history of Earth's climate, the conditions for life around other stars, and the physical character of the space between the stars. That is what happens when you measure something that has never been measured before. The implications propagate through every field that touched the thing you measured. Heliospheric science touched nearly everything. There is also the question of what Voyager is measuring right now, in real time, as it moves deeper into interstellar space at 38,000 miles per hour. Every day, it travels approximately 900,000 miles farther from the Sun. Every data packet it sends back is from a position in interstellar space that no previous measurement has described. The measurements Voyager makes today are not redundant with the measurements it made at the heliopause crossing. The interstellar medium is not uniform. It has structure, density variations, magnetic field gradients, and the overlapping effects of multiple stellar systems, all pushing waves and field distortions into the surrounding medium. As Voyager moves outward, the plasma it is immersed in changes. The density may vary. The magnetic field direction and strength may evolve. Solar plasma tsunamis continue to reach the spacecraft's position as long as the sun's eruptions are powerful enough, and each one provides another precise local measurement of plasma density at a new position in interstellar space. Scientists are building a profile of the interstellar medium along Voyager's trajectory, one measurement at a time. Each new plasma density measurement adds a data point to what will eventually become, if the instrumentation holds out long enough, the first interstellar medium profile along a defined direction in the galaxy. That profile will be invaluable for calibrating models of how the interstellar medium varies on scales smaller than the typical distance between stars. Models of the interstellar medium are built from remote observations that average over large volumes of space. Direct, position-specific measurements from a spacecraft moving through the medium provide a ground truth check on those averaged models, revealing structure that the averaging would otherwise hide. This is slower science than the dramatic crossing event of 2012. There is no single discovery moment where a number comes back 40 times larger than expected. But the accumulation of measurements, position by position, is building a dataset that will be used long after Voyager falls silent to constrain the structure of the local interstellar medium in our corner of the galaxy. What scientists know for certain is that the interstellar medium Voyager is moving through is not structureless. The plasma tsunamis have already shown that it responds to events inside the heliosphere, that our star's eruptions propagate far beyond the heliopause and disturb the surrounding medium. The magnetic field measurements have shown that the interstellar magnetic field has a definite orientation and structure. The density measurements have shown that the medium is denser than pre-crossing models predicted. What scientists do not yet know is how far these properties extend, how quickly they change with distance, and what Voyager will find if it survives long enough to probe deeper into the local bubble's interior. Every year it keeps operating is another year of data from a location that has never been measured before. That data is still coming in, the science is still happening, and the questions it is raising are still worth pursuing to their answers. We have spent a lot of time on the measurements themselves, and on what they mean for heliospheric science. But there is something worth examining more carefully. the process by which scientists became confident in what the measurements were actually telling them. Because the path from raw instrument data to confirmed scientific discovery was not straightforward, it took years, multiple lines of evidence, and genuine scientific debate. When Voyager 1's instruments first started showing the pattern that would eventually confirm a heliopause crossing, the scientific team did not immediately declare that the spacecraft had crossed into interstellar space. The cosmic ray counts were changing in suggestive ways. The particle data was oscillating in ways that suggested the spacecraft was near the boundary. But the key diagnostic that scientists most trusted, the direct measurement of the plasma density that would confirm whether the spacecraft was in the heliosheath or in interstellar space, required a functioning plasma science instrument. And Voyager 1's plasma science instrument had not been working properly since 1980. So, the team was looking at indirect evidence. They could see the cosmic ray counts changing. They could see the magnetic field behaving differently. They could see that the low-energy particle population from the solar wind was dropping dramatically. All of these changes were consistent with a heliopause crossing, but none of them was definitive by itself. The debate in the scientific community about whether Voyager 1 had actually crossed was genuine and sustained. Some researchers argued, based on the available data, that the spacecraft had crossed by mid-2012. Others argued that the data was consistent with Voyager 1 entering a previously unobserved transitional region inside the heliopause, not outside it. Without a direct plasma density measurement that could distinguish between heliosheath plasma and interstellar plasma, the debate could not be resolved. What resolved it was, as we have discussed, the plasma tsunamis. When the solar eruption from March 2013 produced a wave that arrived at Voyager 1 and caused the surrounding plasma to ring at a measurable frequency, the frequency translated into a plasma density far higher than heliosheath values and consistent with interstellar medium values. The crossing was real. The data was definitive. But consider what this means for the process of science. A discovery that would become one of the most significant in the history of space exploration sat in a state of legitimate scientific uncertainty for more than a year. Researchers were examining the same data and reaching different conclusions. The debate was resolved not by someone arguing more cleverly, but by a new piece of data generated by a solar event that nobody planned for, that arrived at the spacecraft's position and provided the measurement the team had been unable to make directly. This is how science actually works at the frontier. You gather data, you interpret it. You find that the data does not fully constrain the interpretation. You wait for new data. The new data arrives from unexpected directions. It resolves the ambiguity. And then you can make the discovery claim with confidence. The Voyager heliopause crossing was eventually confirmed as a genuine scientific discovery. The plasma density measurements from the tsunamis provided the necessary evidence. The scientific community reached consensus. The crossing was accepted, and the anomalous measurements, the plasma density 40 times higher than expected, the magnetic field direction that did not match predictions, became the foundation for a new and better understanding of the heliopause and the interstellar medium beyond it. That process, from ambiguous initial signal to confirmed discovery, took roughly a year. In the history of science, that is extremely fast. In the experience of the scientists who had been working on Voyager for decades, and who suspected what the spacecraft was telling them, a year of uncertainty before definitive confirmation was a long time. Now let us look forward and think about what the next few years of Voyager data might reveal. Voyager 1 is currently in the interstellar medium at roughly 160 astronomical units from the Sun, which works out to approximately 15 billion miles. Every year, it travels roughly 3.5 astronomical units farther from the heliopause. By the time its instruments fail, it will be perhaps another 10 to 20 astronomical units deeper into interstellar space than it is now, depending on how long the instruments hold out. That is a relatively small additional range, compared to the total distance it has already traveled. But each additional measurement matters, because the interstellar medium is not uniform. The plasma density Voyager measured just outside the heliopause may not be representative of the local interstellar medium at slightly larger distances. The magnetic field direction may vary. The cosmic ray spectrum may shift. Every new position in interstellar space that Voyager samples is genuinely new information. The interstellar medium in the local bubble has never been directly measured by an in situ instrument before Voyager crossed the heliopause. Every measurement Voyager makes in interstellar space is a first, adding to what will eventually become the only in situ profile of the local interstellar medium that will exist until the next interstellar mission arrives. Scientists are also watching carefully to see whether any additional plasma tsunami events arrive at Voyager 1 from solar eruptions. Each tsunami event provides a localized plasma density measurement at the spacecraft's current position. A sequence of tsunami measurements at different positions as the spacecraft moves outward would give scientists a profile of how the local interstellar plasma density varies with distance from the heliopause. That profile would test models of the heliopause's influence on the surrounding medium, and would reveal whether the elevated density Voyager measured just outside the boundary is a boundary region effect, or whether it extends deep into the interstellar medium. There is also the magnetic field to watch. Voyager 1's magnetometer is still operating. If the local interstellar magnetic field has any variation in direction or strength along the spacecraft's trajectory, the magnetometer should detect it. Any detected variation would add to our understanding of the local bubble's magnetic structure and would help distinguish between the competing explanations for the heliopause field direction discrepancy. And there is the cosmic ray monitoring. Outside the heliopause, galactic cosmic rays arrive from all directions, but not equally from all directions. The distribution of cosmic ray arrival directions reflects the structure of the local magnetic field and the distribution of cosmic ray sources in the galaxy. Voyager's cosmic ray instruments, operating continuously, are building a statistical picture of how the cosmic ray intensity and directional distribution varies along its trajectory in interstellar space. All of this data, even from an aging, power-limited spacecraft operating at the extreme edge of its design lifetime, is adding to a picture of interstellar space that will be the foundation for heliospheric science for decades. No model of the heliopause, the heliosheath, or the local interstellar medium can be considered complete unless it is consistent with what Voyager has measured. That constraint, the requirement to be consistent with actual direct measurements, is enormously valuable in a field that, before 2012, had only models and remote observations to work with. There is something deeply human about Voyager that deserves to be acknowledged, not in a sentimental way, but as a scientific fact. Voyager 1 is the farthest object from Earth that humanity has ever built and sent out into the universe. Not farthest from the Sun, which is a more commonly cited statistic, but farthest from Earth as well. Since Earth revolves around the Sun, and our distance from Earth is always close to our distance from the Sun on these scales, Voyager 1 is the most distant human-made object in the history of our species, and it is still communicating. The radio transmitter on Voyager 1 operates at a power of roughly 23 watts, about the same as a typical compact fluorescent light bulb. That 23 watts of radio power is spread in all directions from the spacecraft's antenna. By the time the signal reaches Earth, after traveling more than 15 billion miles, the power that arrives at the receiver is almost inconceivably small. The signal arriving from Voyager 1 is so faint that it represents a power of roughly 10 to the negative 21st watts at the receiver, or about 1 sextillionth of a watt. 1 sextillionth. That is a power level roughly 500 million times smaller than the weakest signal a modern smartphone can detect. Receiving Voyager signal requires the largest antennas in NASA's Deep Space Network, dishes 70 meters across and more, pointed precisely at the spacecraft's location. Using extremely sensitive amplifiers, cooled to near absolute zero to reduce electronic noise. The fact that this works at all is a testament to both the engineering of the spacecraft's antenna system, which keeps the radio beam focused toward Earth, and the engineering of the Deep Space Network's giant receivers, which can pull that unimaginably faint signal out of the background noise of the cosmos. When Voyager finally falls silent, it will not be because the spacecraft fails in some catastrophic way. It will simply be because the power output of the radioisotope thermoelectric generators has dropped too low to operate the transmitter while also maintaining the instruments at operating temperatures. The spacecraft will keep moving. It will keep existing. It will just stop talking. At roughly 38,000 miles per hour, Voyager 1 will travel approximately 912,000 miles per day. In a year, that is roughly 330 million miles. In a decade, roughly 3 billion miles. In a century, roughly 30 billion miles, or about a fifth of an astronomical unit more per century. At that rate, it would take roughly 73,000 years to cover the 4 light years to the nearest star system. It will never arrive at another star in any meaningful human sense, but it is heading somewhere in a direction that takes it out of the solar system and into the vast interstellar distances that separate stellar systems. The Milky Way galaxy is roughly 100,000 light years across. Voyager 1 has traveled, in 48 years, roughly 1/600 millionth of the galaxy's diameter. Space is large. We have barely begun. And yet the measurement Voyager made, the first direct sampling of interstellar space, is genuinely one of the most significant scientific achievements in the history of spaceflight. Not because of the distance traveled, though that is extraordinary, but because of what was found there. A boundary more complex than models described. An interstellar medium denser and more magnetically structured than expected. A heliosphere that breathes and leaks and varies by direction in ways that only direct measurement could reveal. A local region of the galaxy shaped by ancient stellar deaths, still in the process of forming new stars from the compressed gas at its edges. And the sun's influence extending past its own boundary, rippling through the interstellar medium in waves generated by solar eruptions, proving that stellar systems are not isolated islands in a featureless ocean, but active participants in the ongoing physics of the galaxy around them. That is what Voyager found. And the signal is still coming in. Each time a data packet arrives at the Deep Space Network's antennas, it carries information from a place that has never been measured before in the history of science. Each measurement of the magnetic field strength, the cosmic ray flux, the plasma density, the oscillations triggered by another solar tsunami arriving from across 15 billion miles, adds to a record that is already irreplaceable and will become the foundation of interstellar science for generations. When scientists decades from now design the missions that will follow Voyager, probe the full 3-dimensional shape of the heliosphere from the outside, map the local interstellar medium in 3 dimensions, and measure the hydrogen walls of other stellar systems with the precision needed to understand astrospheric shielding across stellar populations, they will begin their calculations from Voyager's numbers. Those numbers will be the baseline, the reference point, the one set of direct measurements that existed before any of the rest was possible. That is a lasting scientific legacy of a kind that very few missions in the history of exploration have achieved. Going somewhere for the first time and reporting accurately what you found there, leaving behind numbers that are true, that are precise, and that will be used to understand the universe better for as long as the science of heliospheric and interstellar physics continues. Voyager 1 is still out there, still moving, still, for a few more years, still transmitting. The signal takes more than 22 hours to arrive. When it does, it still carries something worth reading. There is a question that scientists and non-scientists alike tend to ask when they learn about what Voyager found at the heliopause. If our models were that far off, how confident should we be in other models of things we cannot directly visit? It is a fair question, and the answer is nuanced. Models are tools built from physical principles and observational constraints. When new observational constraints become available, the models improve. The fact that the heliospheric models before Voyager's crossing were wrong about the plasma density, the magnetic field direction, and the detailed structure of the heliopause boundary does not mean that all models of remote environments are unreliable. It means that models of environments that have never been directly sampled should be held somewhat loosely, with awareness that direct measurement might reveal surprises. The plasma density discrepancy was not a failure of physics. The physics of how plasma behaves was well understood. The discrepancy was a failure of the assumed initial conditions and boundary conditions that were plugged into perfectly good equations to produce predictions. The interstellar medium just outside the heliopause had different properties than the models assumed, partly because those assumed properties were derived from remote observations that could not distinguish the near-boundary region from the broader interstellar medium along the line of sight. When Voyager provided direct, local measurements, the physics still worked. The plasma behaves like plasma. The magnetic field behaves like magnetic fields behave. What changed was the numbers that go into the equations, not the equations themselves. And once the measured numbers were used as inputs, the models became much better. This is actually a reason for confidence, not alarm. The process of improving models by incorporating direct measurements is working exactly as it should. Before Voyager, heliospheric scientists were doing the best they could with the data available. After Voyager's crossing, they did better, because they had better data. Science progressing through the accumulation of direct evidence and the revision of models in light of that evidence is science functioning correctly. The lesson for other models of remote, unmeasured environments is similar. Our current models of the interstellar medium at larger distances from the Sun, the structure of the local bubble at positions we have not directly sampled, the properties of astrospheres around other stars, are all built on the best available data and the best physics we know. They will improve as new data arrives. Some of the improvements will be small refinements. Others, like the plasma density discovery at Voyager's crossing, may turn out to be qualitative revisions that change the entire picture. That possibility is not a weakness of science. It is how science is supposed to work. The willingness to be surprised is one of the most important qualities in a good scientist. Being surprised by data means you are measuring something real, not just confirming what you assumed going in. Voyager surprised its scientists. They measured it, they investigated it, they revised their models, and the field is better for it. The next interstellar probe will almost certainly deliver more surprises. The universe, it turns out, is more complicated and more interesting than any particular model we have built to describe it. That is not discouraging. That is one of the best things about actually going to places and measuring them directly. And finally, let us be precise about what makes the Voyager mission singular in the history of exploration. Not just in terms of scientific results, but in terms of what it represents as an achievement. Human beings have been exploring for as long as recorded history. We have crossed oceans on wooden boats. We have climbed the highest mountains. We have reached the poles of our own planet. We have sent spacecraft to every planet in the solar system, landed on the Moon and on Mars, flown past Pluto, and orbited every gas giant. All of these are extraordinary achievements. But Voyager is the first time we have sent an instrument past the outer boundary of our solar system and received a report of what it found there. Not a simulation, not a model, not a theoretical prediction, an actual measurement from the actual place. For the first time in the 4 billion year history of life on this planet, and in the 50,000 year history of anatomically modern humans, something we built reached interstellar space and told us what it found. That is a genuinely new kind of thing in the history of our species. The numbers Voyager sent back are not just scientifically interesting. They are the first direct evidence that beings from Earth have reached beyond the solar system and returned information about what lies beyond. Future generations, if they remember anything about this era of science and exploration, will remember that the first contact with interstellar space happened in the early 21st century, conducted by a spacecraft the size of a compact car, powered by a device barely larger than a basketball, transmitting on 23 watts from more than 15 billion miles away. And what it found will be the starting point from which everything that follows begins. Before we close this story, there is one more thing worth examining: the instruments Voyager carries, and what each of them has contributed to what we now know. Because the story of how a spacecraft with 1970s technology measured interstellar space is partly a story about instrument design, and partly a story about scientific improvisation and creativity under constraint. Voyager 1 launched with 10 scientific instruments. Several of them had already been shut down to conserve power by the time the spacecraft reached the heliopause. The imaging cameras, which produced the iconic photographs of Jupiter, Saturn, and their moons, were powered down in 1990 because they required too much electricity to operate, and because there was nothing left to photograph in the darkness of the outer heliosphere. What remained operating through the heliopause crossing were four main science instruments: the plasma wave instrument, the magnetometer, the cosmic ray subsystem, and the low-energy charged particle instrument. Each contributed something essential to the crossing story. The cosmic ray subsystem counted high-energy particles arriving from both inside and outside the heliosphere. Its data provided the first clear signal that Voyager was approaching the heliopause. The count of solar origin particles dropping sharply, while the count of galactic origin particles rose. The pattern was the clearest leading indicator of the crossing before the final confirmation. The low-energy charged particle instrument measured the population of lower-energy particles, the ones most directly associated with the solar wind and the heliosheath. When these counts dropped to near zero after the crossing, they confirmed that Voyager had left the domain of solar wind-dominated space. The magnetometer measured the magnetic field strength and direction continuously. Its data provided the puzzling field direction measurement just outside the heliopause, the one that did not shift as far as predicted. It continues operating today, building the first in-situ profile of the local interstellar magnetic field along Voyager 1's trajectory. And the plasma wave instrument, the one that was not designed to measure plasma density directly, but turned out to be able to do so through the physics of plasma oscillations triggered by solar eruptions, provided the definitive confirmation of the crossing and the measurement of the 40 times higher than expected plasma density. Each of these instruments was designed in the early 1970s. Their designers are in many cases no longer living. The institutions that built them have changed or disappeared. The data they return is being analyzed by scientists using 21st century software and theoretical frameworks that their designers could not have imagined. And yet the physical principles those instruments use, electromagnetic induction for the magnetometer, wave physics for the plasma wave instrument, particle detection for the cosmic ray counters, are timeless. Physics does not change. A good instrument based on solid physical principles, built with sufficient engineering margin, and housed in a spacecraft that can survive decades in space, can outlast every expectation and contribute to science its designers never anticipated. That is the Voyager story, in miniature. Sound physical principles, good engineering margin, willingness to improvise when constraints change, and decades of patience, both from the spacecraft holding together and from the scientists and engineers who kept it operational across the careers of multiple generations. The science that resulted is extraordinary, but it rests on a foundation of careful, rigorous, patient engineering and operations that deserves equal recognition. The signal is still coming in, the science is still happening, and the story of what lies beyond the edge of our solar system is still being written. One plasma oscillation, one magnetic field measurement, one cosmic ray count at a time, from a machine the size of a car that humanity sent into the dark 48 years ago, and that, against every reasonable prediction, is still talking.